Hi, I'm here to explain cache memory and the implementation in modern computers. My name is Vamsi Krishna. We should know what is a cache memory. Cache is a volatile memory located on or near the processor that stores data instructions to serve future requests without going to the memory. One of the main important features of cache is associativity. Associativity can be direct, two-way, four-way, n-way, and fully associative. As we increase the size of a cache level, we increase the associativity also, so that if more number of locations will be available for a address. It is a known fact that caches with more associativity suffer fewer misses. Consider a 4 KB cache. Consider a 4 KB cache, and we go on increasing the associativity. We see a miss rate decreases. Here we see this implementation of cache levels in a CPU. As we go from lower level cache to higher level cache, cost per byte increases and access time decreases. Here we see an example of a multi-processor with a quad core. Cache levels in this process follow inclusivity property. What is an inclusivity property? Inclusivity property states that um, data in L1 should necessarily be in L2 also. And the main advantage is that whenever you are accessing the data after a miss from L1, it can be fetched from L2. L3 is a shared cache that means the data from it can be shared by the other cores and other CPUs. Main memory is also a shared one. Levels of cache. We have till 2013 we have 3 levels of cache, and now L4 being implemented with DRAM technology. L4 is implemented for gaming purposes, um, for high-end design supported process. We see here how we implement EDRAM as a fourth level of cache in a processor. Consider L3 as the last level cache. It stores the data or tags of the L4, that tags of the L4 cache. That means the data to be accessed from EDRAM. In order to maintain accuracy, the tags need to be compared and fetched from EDRAM. EDRAM is a link between CPU and GPU. How we gonna implement this EDRAM? EDRAM is implemented with one transistor, one capacitor. As we use one capacitor, its values decays with time. So in order to maintain a constant value, this needs to be refreshed periodically. And the advantage of this EDRAM being it's a low cost and offers more memory storage. We see a comparison between SRAM and embedded DRAM. And the very most important feature is access time. That is why SRAM has more advantages in higher level caches and EDRAM and the lower level caches. We overcome this drawback of high refresh power in EDRAM by using deadline prediction scheme. Deadline prediction scheme is based on making the line of a cache level dead when it is not accessed for a certain period of time, so that we can reduce the power needed for refreshing the inactive data. This is the quick path architecture implemented in our modern computers. This has fine interconnects between CPUs and memory controllers. These offer high bandwidth. Higher bandwidth in the sense which reflects on accessing the data at a faster rate. These CPUs are implemented based on the shared memory cache and the Snoop protocol. Snoop protocol ensures that the data from either end of the memory 1 and memory 4 are accessed with low latency. Consider an example to elaborate on this architecture, where processor 1 needs data located in the processor 4's memory. A general architecture needs 4 hops. That means 1 to send the data signal, then the processor 4 ensures that other processors do not have any data. Then other processors acknowledge that we don't have any. Then processor 4 sends the signal in the fourth hop to the processor 1. In our architecture, we implement this with the Snoop protocol and cache forwarding technique. Consider we have a local copy of data in processor 3. Here, processor 1, same as above, processor 1 requests the data from processor 4. Processor 1 now sends the signals to all the processors. Then processor 3 immediately sends the data to processor 1. And the next hop, processor 4 makes sure that the data received by the processor 1 is accurate. Thus, we complete the process in 2 hops. We implement this architecture with MESI-F protocol. MESI-F protocol is nothing similar to MESI protocol with an additional state forwarding. Here, a processor with local copy of data is marked name forward state. That means it has a recently accessed time. Recently accessed it. With this truth table, we implement. We can study that a processor in forwarding state enables other process to be in a shared state or invalid state. With the coming to the advantages. Advantages of using this maximizes data transfer performance and minimizes conflicts and misses. This is implemented with RAS features. RAS features in the sense reliability, availability, serviceability. Reliability states that the data we receive are accurate. Availability is a measure that it is available whether it's correct or not. Serviceability states that the time required to repair itself. Coming to the conclusion, this encourages technologies to implement volatile memories as higher level caches with further improvements. This has a main impact on high-end systems in improving bandwidth and latency. These are the references used by me. Thank you.